What if the entire story of our existence, the grand narrative of 13.8 billion years, has a missing first chapter? Not just a few smudged words or a torn page, but the entire prologue, the very first line of creation lost to us. We have pieced together a truly majestic tale, a cosmic saga of how stars ignited from primordial gas, how galaxies spun themselves into celestial tapestries, and how on one quiet world life looked up and began to wonder. We trace our own atoms back through the hearts of dying suns, back through the nebular clouds that birthed them back to a universe smaller than a grain of sand yet containing everything. We call this incandescent beginning the Big Bang. It is the single greatest story we have ever told ourselves, the foundational truth of modern cosmology. And yet it is a story that begins in darkness. Not the darkness of empty space, but the impenetrable brilliance of a cosmic furnace. Our most powerful telescopes, our most sensitive instruments, can only peer back so far into the past. They journey across unfathomable distances, gathering the ancient light of galaxies that have long since ceased to exist, their photons travelling for eons to reach our eyes. With this fossil light, we have constructed a timeline of cosmic evolution, watching the universe grow cool and structure itself. We can see back to a time when the cosmos was a toddler, a mere few 100 million years old, just beginning to switch on its first stellar lights. We can push even further past the era of the first stars, past the formation of the first atoms, to a single breathtaking precipice in time. Here we encounter a wall, not a physical barrier but a curtain of light. This is the cosmic microwave background, the oldest light in the universe, an afterglow of creation that permeates all of space. It is a stunning discovery, a baby picture of the cosmos when it was just 380,000 years old, a uniform superheated fog of hydrogen and helium plasma. In this image we can see the subtle seeds of all future structure, the faint temperature variations that would over millions of years blossom into the vast clusters of galaxies we see today. It is a Nobel Prize-winning triumph, a snapshot that confirms our cosmic origins with breathtaking precision. But it is also a frustratingly opaque boundary. Before this moment, the universe was so hot and so dense that it was a sea of charged particles, a plasma that trapped light itself. Any photon of light emitted was immediately scattered, reabsorbed and re-emitted in a chaotic, blinding fog. Light could not travel freely. The universe was in essence a star, and so our story told in the language of light stops here. The entire history of the universe before this moment, the first 380,000 years of its existence, is completely hidden from our view. This is the ultimate cosmic irony. The very origin of light is an event we can never witness with light. The Big Bang itself, the cataclysmic first second, the first minute, the first millennia, all of it transpired behind this impenetrable plasma curtain. What happened in those crucial formative moments? How did a universe of perfect uniform energy spontaneously break and give rise to the particles that make up you and me? What was the nature of the unimaginable explosion that ignited space and time? These are the most profound questions we can ask, and they are questions that electromagnetism, the force that governs light, is fundamentally incapable of answering. For generations, it seemed this primordial chapter would remain forever unread, a realm accessible only to mathematical theory and philosophical speculation. But what if there was another way to see another language in which the universe writes its history? A messenger so fundamental, so ghostly and persistent, that it could travel unscathed from the very instant of creation, passing through that fiery plasma wall as if it were not even there. To understand this possibility, we must first reimagine the very stage upon which this cosmic drama unfolds. We are accustomed to thinking of space as a void, an empty passive backdrop. For centuries, this was our view, a static, three-dimensional grid, the absolute and unchanging arena in which objects moved. But a little over a century ago, a young patent clerk named Albert Einstein offered a vision that shattered this old reality forever. He revealed that space is not separate from time. They're interwoven into a single dynamic four-dimensional continuum space-time. And this fabric is not rigid. It is a supple active entity shaped and warped by the presence of matter and energy. Imagine a vast taut membrane stretching to infinity. A star, a planet, even your own body creates a depression in this fabric, a gentle curve. This curvature, This geometry of space-time is what we experience as gravity. It is not a mysterious force pulling us from a distance, but the very shape of the universe guiding our motion. An orbiting planet is not being pulled by the sun. It is following the straightest possible path through the curved space-time created by the sun's immense mass, like a marble rolling around the inside of a bowl. This was Einstein's masterwork, the theory of general relativity. It transformed gravity from a force into the language of cosmic architecture. And within that new language, he found a truly startling prediction. If space-time can be bent, he reasoned it must also be able to ripple. If a massive object were to accelerate to move violently, it should not just create a static dimple in the fabric of reality. It should create a disturbance, a vibration that propagates outward at the speed of light. These are not waves moving through space like sound waves move through air. They are waves of space itself. They are gravitational waves, and they are one of the most bizarre and wonderful concepts in all of physics. As a wave passes by, it literally stretches and squeezes the geometry of space, and with it the flow of time. The distance between 2 points will oscillate, first expanding and then contracting. An object in its path would be subtly compressed in one direction, while being elongated in another. The effect is impossibly small, a distortion far tinier than the width of a single atomic nucleus. For decades, Einstein himself wondered if they were merely a mathematical artifact, a phantom in his equations too faint to ever be detected. For a century, these ripples remained a theoretical ghost. We had indirect evidence of their existence, watching the orbits of dense neutron stars decay, in perfect accord with the energy being carried away by these invisible waves. But to directly feel the shudder of space-time itself seemed a task for a future civilization. It would require an instrument of almost unimaginable sensitivity, a device capable of measuring a change in distance 1,000 times smaller than a proton over a span of several kilometers. It was a challenge so immense it bordered on the absurd, and yet we built them. We constructed colossal L-shaped interferometers, firing powerful lasers down miles-long vacuum tubes. These machines were designed to listen, not for sound, not for light, but for the faint stretching sigh of a passing gravitational wave. And then on September 14th, 2015, the universe finally spoke in this new language. A tremor washed over the Earth, a fleeting vibration that stretched and squeezed our planet and everything on it by a microscopic amount. It was detected by twin observatories in the United States, a signal so clear, so perfectly matched to the predictions it was unmistakable. We had heard the sound of two black holes each 30 times the mass of our suns spiraling into one another, in a final violent dance a billion light-years away. In the last fraction of a second of their existence, they merged, converting 3 suns worth of mass directly into a pure blast of gravitational energy, a space-time storm that warped the cosmos. That signal, that chirp, was the birth of a new astronomy. For the first time, we were no longer just watching the universe. We were listening to it. Since that day, we have heard dozens more of these events, the cataclysmic mergers of black holes, the explosive collisions of neutron stars, events that forge the heaviest elements in the universe, like gold and platinum. Each detection gives us a new and intimate way to understand the most extreme phenomena in the cosmos. These waves are not blocked by gas or dust. They travel directly from their source to us, carrying an unblemished story of their violent origins. They are a new sense, allowing us to perceive the universe not through its light, but through its very vibrations. And this brings us back to that impenetrable wall at the dawn of time. Back to the missing first chapter. The same property that allows gravitational waves to travel unimpeded from a distant black hole merger also applies to the very beginning of the universe. That fiery plasma fog, opaque to any form of light, is completely transparent to gravity. While photons were being endlessly scattered in the primordial soup, any gravitational waves generated in the Big Bang would have sailed right through, travelling freely across the entire expanse of cosmic history. This is the central breathtaking promise of this new science. The universe's most violent and energetic event must have been, by its very nature, the most powerful generator of gravitational waves of all time. The Big Bang should not have been a silent event. It should have been a deafening roar, a gravitational cataclysm that shook the newborn fabric of space-time to its very core. The The inflation of the universe, the theoretical instant of hyperexpansion, in the first trillionth of a trillionth of a trillionth of a second, would have stretched quantum fluctuations into a cascade of space-time ripples. The collisions of cosmic strings, the phase transitions of exotic forms of matter, every chaotic high-energy process in that nascent moment would have left its indelible signature, its unique vibrational fingerprint on the geometry of reality. These are not the sharp, transient chirps of merging black holes. These would be something else entirely. A primordial gravitational wave background. A constant faint stochastic hiss of ancient ripples coming from all directions in the sky. A symphony of creation's first moments still echoing through the cosmos today. This is the Holy Grail. It is a message that has been travelling towards us for 13.8 billion years. A message that predates every star, every galaxy, every atom. It is the only physical relic, the only direct fossil record that could tell us what happened in the first fraction of a second of the universe's life. It is not a picture of the afterglow. It is the echo from the fire itself. Imagine what we could learn. By studying the properties of this background, its strength at different frequencies, its patterns across the sky, we could test our most fundamental theories about the universe's birth. We could directly observe the energy scale of cosmic inflation, confirming a theory that has until now lived only in the realm of mathematics. We could peer into a realm of physics so extreme it is thousands of trillions of times more energetic than anything we can create in our largest particle accelerators. We could potentially discover entirely new particles and forces that existed only in that primordial furnace. We would be reading the source code of the cosmos. We would be opening that lost first chapter. We would be witnessing in the most direct way imaginable the birth of time and space. This is the quest we now find ourselves on. It is a search for a signal so faint, so buried in the noise of the cosmos and our own terrestrial activity, that detecting it represents one of the greatest technological challenges ever undertaken by humanity. It pushes the boundaries of engineering, of quantum mechanics, of data analysis. It requires a patience and a vision that spans generations of scientists. We are building new instruments both on the ground and in space designed with the express purpose of capturing this whisper from the dawn of time. We are attempting to hear the gravitational reverberations of the Big Bang. This is not merely a search for another astronomical phenomenon. It is a search for our ultimate origin story told in the oldest, purest language the universe has to offer. It is a transcendent journey back to a moment before light itself existed, a quest to find the ripples left behind by the single greatest event in history. For if we can detect them, if we can decode the information they carry, we will have finally breached that final wall. We will have found the key to unlocking the secrets of the first second, and we will gaze upon the face of creation. The question is no longer whether the message is out there travelling through the cosmos on its epic journey towards us. The only question is, are we clever enough to finally hear it? What does it mean for a universe to be born? Is it a singular moment, a flash of impossible light? Or is it a process, an unfolding story written in a language we're only just beginning to decipher? For most of human history, this question belonged to philosophy, to religion. But a little over a century ago, it fell into the hands of a young physicist who dared to reimagine the very stage upon which reality plays out. His name was Albert Einstein, and he gave us a new cosmos. It was not the rigid clockwork arena of Isaac Newton, a static backdrop for the dance of planets and stars. No, Einstein's universe was a living, breathing entity. He imagined a four-dimensional world, a fusion of space and time he called space-time, and he saw that it was not a stage but an actor. Matter and energy, he proposed, tell space-time how to curve, and in turn that curvature tells matter and energy how to move. This is gravity. Not a mysterious force reaching across the void, but the very shape of the universe itself, warped and dimpled by the presence of everything within it. You're not held to the earth by an invisible tether, but by sliding down a valley in space-time carved by our planet's immense mass. The moon is not tethered either. It is simply following a straight line through a cosmic terrain that has been bent into a circle. It was a vision of breathtaking elegance, a complete overthrow of our most fundamental intuitions about existence. This theory, general relativity, became the bedrock of modern cosmology, a mathematical key to unlock the universe's grandest secrets. But hidden within its complex equations was a prophecy, a prediction so strange, so profound, that even Einstein himself found it difficult to fully accept. If space-time is a dynamic fabric, then it should be able to ripple, it should quiver. When the most massive, most violent objects in the cosmos accelerate and collide, they should not do so quietly. They should send shudders through the geometry of reality itself, gravitational tremors propagating outwards at the speed of light. These are gravitational waves, not light, not matter, not energy, travelling through space, but ripples in the very structure of space. Imagine dropping a stone into a perfectly still cosmic pond. The waves that spread from that impact are not made of water. The waves are the water, its very form disturbed and then resettled. Now imagine that pond is the entire universe, and the stones are not pebbles, but colossal objects locked in a death spiral. Two black holes, each with a mass of 30 suns whirling around each other hundreds of times a second before merging in a final cataclysmic annihilation. The energy released in that final fraction of a second is more powerful than all the light from all the stars in the observable universe combined, yet it is released almost silently, not as a flash of light, but as a violent storm in the fabric of space-time. These waves stretch and squeeze everything they pass through. As a wave washes over you right now, you're being infinitesimally stretched taller and squeezed thinner, then squeezed shorter and stretched wider. The effect is so small, so impossibly subtle, that the change in your height is less than the width of a single atom. Detecting such a whisper from the cosmos was for a century considered a challenge on the verge of impossibility. It was a ghost in the machine of the universe. But this prophecy of space-time ripples born from Einstein's mind pointed toward a deeper truth. If the universe is dynamic, if it can bend, and if it can ripple from the violence of its inhabitants, then what of its own birth? What kind of wave would be created by the most violent event of all, the beginning of everything? To even ask that question, we must journey back to the origin point guided by a second great pillar of modern cosmology, the Big Bang. This too is a theory born from Einstein's equations, a startling implication that the universe was not eternal and static but had a beginning. Looking out into the cosmos, we see galaxies rushing away from us in all directions. The further they are, the faster they recede. This is the great cosmic expansion. If we run that film in reverse, we find that everything we see, every star, every galaxy, every atom was once closer together. Rewind far enough and everything collapses into a single point, a state of unimaginable temperature and infinite density, a singularity. This was not an explosion in space, a misconception we must abandon. It was the explosion of space. There was no outside for it to expand into. In the beginning, all of space, all of time, all of matter and energy was compressed into a volume smaller than a grain of sand. From this primordial furnace, our universe began its epic journey. In the first few minutes, the temperature was in the billions of degrees, a seething quark-gluon plasma, too hot for even protons and neutrons to form. As space expanded, it cooled. The fundamental forces of nature crystallized out of a unified whole one by one. Protons and neutrons coalesced, then captured electrons to form the first simple atoms, hydrogen, helium, a trace of lithium. For 380,000 years, the cosmos was an opaque fog, a blistering inferno where light was trapped endlessly, scattering off a sea of charged particles unable to travel freely. Then the universe cooled to a critical threshold. The fog cleared. For the first time, light broke free and streamed across the cosmos, an event known as recombination. This is the oldest light we can ever hope to see. The afterglow of creation, which has been travelling toward us for 13.8 billion years. It surrounds us today, stretched by the expansion of space into the microwave part of the spectrum. We call it the cosmic microwave background, or the CMB. When we map it, we are seeing a baby picture of the universe, a snapshot of the moment it first became transparent. This fossil light is the triumphant confirmation of the Big Bang model, a stunningly successful theory that explains the expansion of the universe, the abundance of the light elements, and the existence of this ancient afterglow. It is the standard story of our cosmic origins, a tale of cooling and structure of gravity slowly pulling together the first atoms into gas clouds, which collapsed to ignite the first stars which gathered into the first galaxies. It's a beautiful, powerful story, and for decades it seemed complete. But as our observations grew more precise, tiny cracks began to appear in this magnificent theoretical edifice. Puzzles emerged, deep paradoxes that the standard Big Bang model for all its successes could not explain. The universe, it seemed, was too perfect, too special. The first and most profound of these puzzles is what cosmologists call the horizon problem. Look again at that baby picture of the universe, the cosmic microwave background. What it reveals is a cosmos of astonishing uniformity. The temperature of the light coming from one patch of the sky is almost exactly the same as the temperature from the opposite patch of the sky. To one part in 100,000, the early universe was in perfect thermal equilibrium. Why is this a problem? Because those two opposite regions of the sky are separated by nearly 28 billion light-years today. When that ancient light was first released, the universe was young. There simply hasn't been enough time in the entire history of the cosmos for a signal travelling at the maximum possible speed, the speed of light, to have gone from one region to the other. They could never have been in causal contact. They could never have exchanged heat to even out their temperatures. It's like finding two people on opposite sides of a vast, impassable desert who have never met or communicated in any way, yet somehow they have the exact same body temperature, down to 1,000th of a degree. It defies all logic. It suggests they were once in contact, but the standard Big Bang model provides no opportunity for that to happen. The universe appears to have a shared history that its own history forbids. This points to a fundamental flaw in our understanding of that first moment. Then there is the flatness problem, a conundrum of cosmic fine-tuning so extreme it borders on the absurd. According to general relativity, the geometry of the universe can take one of three forms. It can be closed, like the surface of a sphere, in which case it would eventually stop expanding and collapse back on itself in a big crunch. Or it can be open, like the surface of a saddle, destined to expand forever, growing colder and emptier until it suffers a big freeze. The third option is the critical, perfectly balanced case in between a flat universe. This is the universe we observe. To an incredible degree of precision, our universe is geometrically flat. The issue is that this flat state is wildly, violently unstable. Any tiny deviation from perfect flatness in the first moments of the Big Bang would have been magnified exponentially by cosmic expansion. For the universe to be as flat as it is today, the initial density at 1 second after the Big Bang had to be tuned to the correct value to an accuracy of 15 decimal places. It is the equivalent of balancing a sharpened pencil on its point and having it remain perfectly upright for 13.8 billion years. A gust of wind, a slight tremor, any imperfection, and it would have toppled. Our universe should not be flat. It should have either collapsed or flown apart into desolate emptiness billions of years ago. Yet, here we are. The standard model offers no explanation for this miraculous balancing act. It simply accepts it as an initial condition, an inexplicable feature of the way things began. And there were other problems, like the absence of strange predicted relics called magnetic monopoles, which should have been forged in the primordial heat but are nowhere to be found. Together, these puzzles painted a troubling picture. Our celebrated story of creation was not wrong, but it was profoundly incomplete. It was like starting a novel at chapter 2. The main events were there, but the setup, the crucial prologue that explained why the characters and the setting were the way they were, was missing entirely. Cosmology was facing a crisis. We needed a new idea, something to explain the universe before the Big Bang we knew. We needed a genesis for our genesis. In 1980, a young physicist named Alan Guth proposed a solution. It was an idea born from particle physics, but it would revolutionize cosmology. It was radical, audacious, and at first glance utterly unbelievable. He called it cosmic inflation. Guth suggested that the standard leisurely expansion of the Big Bang was preceded by something far more dramatic. He theorized that in the first sliver of a second, a period of time so short it makes a nanosecond seem like an eternity, the universe was dominated by a bizarre form of energy, a false vacuum, which possessed a powerful repulsive gravity. This anti-gravity didn't pull things together, it pushed everything apart with unimaginable force. During this period from roughly 10 to the minus 36 to 10 to the minus 32 seconds after its birth, the universe underwent a period of exponential hyperaccelerated expansion. It didn't just get bigger, it doubled in size and then doubled again and again and again at least 100 times over. In this fleeting instant, a region of space smaller than a proton was stretched to a volume larger than the entire observable universe today. Then just as suddenly this inflationary energy decayed, dumping its incredible energy into a firestorm of particles and radiation. This massive release of energy is what we traditionally call the Big Bang. Inflation wasn't a replacement for the Big Bang, it was the engine that ignited it. This single explosive idea solved the great cosmic conundrums with breathtaking elegance. The horizon problem vanished. The entire observable universe we see today from one edge to the other originated from a single infinitesimally small patch before inflation began. This patch was so tiny that it was in perfect causal contact. Everything had time to settle to a uniform temperature. Then inflation took this smooth, tiny region and expanded it to astronomical proportions faster than the speed of light. The two people in the desert mystery. They were standing shoulder to shoulder before the desert was instantly created between them. The flatness problem was also solved. Imagine the curved surface of a balloon. If you inflate that balloon to the size of the Earth, your local patch of its surface will appear perfectly flat. Inflation did the same to the universe. It took any initial curvature the universe might have had and stretched it out to such an immense scale that our observable cosmic horizon now appears perfectly flat. The pencil isn't balanced on its tip. Inflation hammered the entire table flat. The missing magnetic monopoles, they were created before inflation, but the exponential expansion diluted them, spreading them so far apart that the odds of finding even one in our observable cosmic volume are practically zero. Inflation was a theoretical masterpiece, a beautiful and compelling prologue to our standard cosmic story. It explained why the universe began in such a special, finely tuned state. But for all its elegance, it remained just that, a brilliant idea, a compelling story. Science demands more. It demands evidence. It requires a testable prediction, a unique fingerprint that only inflation could have left behind. And inflation does make such a prediction. A prophecy of its own. Think about that period of hyperacceleration. The stretching of space-time on such a violent quantum scale would not have been a smooth process. The very fabric of reality would have been churned, twisted, and snapped taut. This process, the most energetic event in the history of the cosmos, would have generated an immense sea of gravitational waves. These would not be the fleeting ripples from two colliding black holes. These would be primordial, stamped into the universe at the moment of its creation. A stochastic background of gravitational waves, a cosmic hum reverberating from the first instant of time. These primordial ripples would be a permanent scar left on space-time, a smoking gun that would prove inflation truly happened. Finding them would be like finding the fossils of the Big Bang itself. It would allow us to peer beyond the wall of the cosmic microwave background, beyond the first light into the inferno of the first fraction of a second. We would no longer just be seeing the afterglow of creation. We would be hearing the echo of its first violent breath. The hunt was on for the ripples of creation, undefined. And so the theory was pristine, a perfect mathematical jewel. It whispered of a universe born in a cataclysm of stretching space, a universe that should be ringing ever so faintly with the aftershocks of its own violent birth. But to go from a beautiful equation on a blackboard to hearing that sound across 13.8 billion years, that was a chasm of impossibility. The echoes of creation were predicted to be so faint, so utterly diluted by cosmic expansion, that detecting them seemed a fantasy, a fool's errand. The challenge was a confrontation with the very scale of existence. How do you build a seismograph for the universe itself? How do you measure a vibration that warps the rigid stage of reality but by an amount infinitesimally smaller than a single atom? For decades, this was the question that haunted the fringes of physics. The first attempts were bold, almost primitive acts of defiant hope. In the 1960s, a physicist named Joseph Weber constructed giant aluminum cylinders weighing several tons apiece, which he claimed were cosmic bells. He believed they would resonate, literally ringing with a quantifiable shudder when a gravitational wave passed through them. He even claimed to have found signals' simultaneous vibrations in detectors 1,000 kilometers apart. For a breathtaking moment, it seemed the door had been flung open. But his results could never be replicated. The signals vanished under stricter scrutiny, phantoms in the noise. The scientific community, once intrigued, grew deeply skeptical. The quest for gravitational waves became a kind of cautionary tale, a lesson in the seductive allure of seeing what you wish to see. The entire field was nearly abandoned, relegated to a theoretical curiosity. It was clear that a simple bell, no matter how large, would never be sensitive enough to hear the true whispers of the cosmos. A radically new kind of ear was needed. The idea that finally emerged was both ludicrously simple and technologically terrifying. It was born from a 19th century experiment designed to measure the ether, a phantom medium once thought to carry light through space. The concept was called interferometry. You take a beam of pure laser light and split it in two. You send these two twin beams down perfectly perpendicular tunnels, each several kilometers long, at the end of which are flawless mirrors. The beams reflect travel back and are recombined. If the arms are of precisely equal length, the light waves should meet in a state of perfect cancellation, a dance of choreographed self-destruction. The detector should see nothing but darkness. But if a gravitational wave were to pass through the Earth, it would stretch one arm of the detector while squeezing the other, subtly, almost imperceptibly altering the travel time for each laser beam. One path would become momentarily longer, the other shorter. When the two beams recombined, they would no longer be in perfect step. Their delicate dance of cancellation would be broken. A flicker of light would escape the darkness, a signal born from a ripple in space-time. This was the blueprint for LIGO, the Laser Interferometer Gravitational Wave Observatory. It was a project of such audacious ambition that many deemed it insane. It demanded two identical facilities 3,000 kilometers apart, one nestled in the arid plains of Washington state, the other amidst the pine forests of Louisiana. This vast separation was crucial, a way to distinguish a true cosmic shudder from a local tremor like a passing truck or a distant earthquake. Only a signal that arrived at both detectors travelling at the speed of light could be a genuine gravitational wave. The engineering required was on a scale bordering science fiction. The 4-kilometre-long arms were not just tunnels, they were among the most perfect vacuums ever created on Earth, ensuring the laser light would not be disturbed by a single stray molecule. The mirror's objects of surreal perfection were polished so precisely that their surfaces deviated by less than the diameter of a few atoms. They were suspended by threads of fused silica glass, creating a multi-stage pendulum system, a gravitational gyroscope designed to isolate them from the ceaseless vibration of the planet itself. LIGO was designed to be the quietest, stillest place in the known world. Every possible source of noise had to be hunted down and silenced. Scientists monitored the rumbling of distant ocean waves crashing on the shore, the seismic hum of the Earth's crust, the thermal vibration within the atoms of the mirrors themselves. They were building an instrument not just of physics but of profound silence. They were attempting to engineer a pocket of absolute stillness in the middle of a noisy, trembling world, all to hear a whisper from the depths of space. And the scale of that whisper is where the mind truly begins to falter. The change in the length of those 4-kilometre arms that LIGO needed to detect was just 1/10,000th the width of a single proton. Let that sink in. It is a measurement so fine it has no earthly equivalent. It is like measuring the distance to the nearest star 4 light-years away, and being able to detect a change in that distance smaller than the thickness of a human hair. This was the monumental task they set for themselves. For years, the project was a subject of immense controversy. It cost hundreds of millions of dollars. It employed hundreds of the world's brightest minds. And for decades after the machines were first switched on, they delivered exactly what their critics had predicted: an unbroken, deafening silence. They listened to the cosmos, and the cosmos, it seemed, had nothing to say. The teams refined, they upgraded, they pushed the technology to its absolute limits, battling against the persistent noise of our own world, chasing a signal that, for all they knew, might never come. The silence was a test of faith, a long, dark night of the scientific soul. Then, on September 14th, 2015, the universe finally spoke. At the newly upgraded Advanced LIGO facility in Louisiana, a strange signal appeared traced out on a computer screen. 7 milliseconds later, it arrived at the detector in Washington. It was clean. It was powerful. It was utterly unambiguous. It was not the rumble of a truck or the whisper of the wind. It looked exactly like the waveform that theorists had predicted for decades. A rising oscillation increasing in frequency and amplitude, a sound that, if translated into the range of human hearing, would be a simple rising chirp. It lasted less than a quarter of a second. But in that fleeting moment, everything changed. The data was almost too good to be true. For months, the LIGO team, now joined by their European counterparts at the Virgo detector in Italy, pored over the signal trying to disprove it to find any other explanation. They checked every system, every sensor, every line of code. There was no other explanation. This was it. They had heard the sound of 2 black holes, cosmic behemoths, each about 30 times the mass of our Sun, locked in a death spiral, a billion light-years from Earth. For eons, they had circled each other partners in a silent gravitational waltz. In the final moments of their union, they were whipping around each other at more than half the speed of light, warping space-time so violently that the energy they radiated away as gravitational waves was for an instant more powerful than all the light from all the stars in the observable universe combined. Then they merged into one. The chirp was the sound of their collision, the ringing of space-time itself as it settled from this cataclysmic impact. The ripple from that event had travelled across the cosmos for over 1 billion years, growing ever fainter, ever more stretched until it finally washed over the Earth, and for a fraction of a second gently squeezed and stretched the arms of 2 machines built for this exact purpose. Humanity had for the first time felt the universe move. The announcement when it came was a thunderclap in the world of science. A century after Einstein had predicted them, gravitational waves were no longer a theory. They were real. We had opened a new sense, a new way of perceiving reality. For all of human history, our view of the cosmos had been defined by light. We were cosmic voyeurs, passively watching photons that had travelled across space to strike our telescopes. But light can be blocked by dust and gas. It cannot escape the crushing gravity of a black hole. It cannot show us the universe as it was in its very first moments. Gravitational waves are different. They are not light. They are disturbances in the fabric of reality itself. They travel unimpeded through anything and everything, carrying pristine information from the most violent and hidden corners of the cosmos. We were no longer just looking at the universe. We were listening to it. We had grown ears, and the symphony that followed was breathtaking. The first chirp was just the opening note. Soon LIGO and Virgo were hearing a drumbeat of cosmic collisions. Dozens of black hole mergers revealing a population of stellar phantoms far more massive and common than we ever imagined. Then came the crowning achievement of this new era. In August of 2017, the detectors picked up a new sound. Not a short, sharp chirp, but a long rising tone lasting for over a minute. It was the sound of 2 neutron stars, the ultra-dense corpses of massive stars spiralling into one another. And this time there was a flash. Telescopes around the world scrambled to find the source. They saw it a kilonova, a spectacular explosion that erupted from the wreckage of the collision. For the first time, we saw and heard the same cosmic event. We witnessed in real time the alchemical forge where the universe creates its heaviest elements. The gold in your jewellery, the platinum in your electronics. We watched it being born in the heart of a stellar cataclysm. It was the dawn of multi-messenger astronomy, a unification of sight and sound that fulfilled the wildest dreams of the generations of scientists who had paved the way. The success was total, a triumph of human ingenuity and persistence that had cracked open a new reality. But even as the celebrations echoed around the world, the scientists knew that this was in a profound sense just the beginning. These discoveries, as revolutionary as they were the product of listening for the loudest, most violent shouts in a universe that is otherwise almost silent. Merging black holes and neutron stars are the thunderclaps of a cosmic storm. They are spectacular, they are informative, but they are not the sound the quest had originally set out to find. They were in many ways just practice for the real performance. The original target, the Holy Grail that had motivated the entire enterprise, was not a singular event, but a constant underlying hum. A sound woven into the very background of existence. The whisper of the Big Bang itself. This is the grand pivot in our story, from the visceral and the immediate to the subtle and the eternal. The gravitational waves from black hole mergers are like feeling the rumble of a freight train as it thunders past your house. It's a powerful, transient, unmistakable event. But the relic gravitational waves from the Big Bang are entirely different. They are like standing on a mountain miles away and trying to hear the collective hum of a distant city. It's not one sound, but a million sounds, blended together into a constant directionless background noise. This cosmic gravitational wave background, or CGB, isn't a chirp. It's a form of cosmic static, a hiss, that permeates every cubic centimetre of space, an ocean of ripples left over from that first explosive moment of inflation. It's the oldest light in the universe, but it's not light at all. It's the oldest sound. And it carries a message found nowhere else. Frozen into this faint stochastic crackle is a unique signature, a specific pattern of polarization that could only have been imprinted by the quantum fluctuations of an inflationary epoch. It's a fossil, not of bone, but of space-time, a direct photograph of the universe when it was less than a trillionth of a second old. Finding this signal would not just confirm inflation, it would give us a portal into the physics of creation itself, and here we confront the next great wall of impossibility. The magnificent machines we built LIGO and Virgo, the technological marvels that achieved what was once thought unattainable, are almost completely deaf to this primordial sound. The reason is a matter of frequency of cosmic pitch. Black hole mergers are high-frequency events. The final moments of their spiral create waves that oscillate hundreds of times per second, a frequency well within the range that ground-based detectors are designed to hear. But the primordial gravitational waves from inflation are a different beast entirely. They were born with an incredibly high frequency in that tiny hot early universe. But then for 13.8 billion years they have been stretched by the relentless expansion of space itself. Their wavelengths have been pulled and elongated, transforming their frantic high-pitched scream into a deep subsonic hum. Their frequencies are now incredibly low with wavelengths spanning light years. They oscillate not hundreds of times a second, but perhaps once every few minutes or hours or even years. For an instrument like LIGO, which is anchored to the vibrating Earth and designed to listen for rapid changes, this slow, majestic swelling of space-time is utterly invisible. It is lost in the low-frequency noise of our own planet's geology. It's like trying to weigh a single feather on a truck scale during an earthquake. The tool is simply wrong for the job, so we find ourselves in a familiar yet more daunting position. We have triumphed. We have conquered a challenge that spanned generations. We have learned to hear the universe. But the very first sound, the message we have sought from the beginning, still eludes us. The echoes of creation are all around you right now, passing through this room, through your body, a constant silent tide. But listening to it requires a new kind of audacity. It requires us to build an observatory not on the Earth, but in the perfect silence of space itself. It demands an instrument not kilometers across, but millions of kilometers across. The quest to hear the Big Bang forces us once again to dream on a cosmic scale. And so we stand before this great glowing wall of light. The cosmic microwave background, a relic from a time when the universe was a mere infant just 380,000 years old. It is the oldest picture we will ever possess, a snapshot of the cosmos, on the verge of becoming everything we know. We have learned to read its subtle temperature variations, the faint blotches of warmer and cooler gas that seeded the great galaxies. For decades we believed this was its primary story. But within that ancient light, a deeper, more secret language was encoded, a message written not in heat, but in the very fabric of the light itself. To understand it, you must think of a ray of light not just as a particle, but as a wave oscillating, vibrating as it travels through space. Ordinarily, the light from a source like the sun is a chaotic jumble vibrating in every possible direction at once. But light can become organized. It can become polarized. Imagine a rope tied to a distant wall. If you shake it randomly, you create a messy confusion of waves. But if you shake it purely up and down or purely side to side, you've created polarized waves, each one vibrating in a single, unified plane. The ancient light of the CMB underwent a similar process of organization. As this primordial radiation streamed through the hot, dense plasma of the infant cosmos, it scattered off free-floating electrons like pinballs ricocheting in a cosmic arcade. This final scattering event at the very moment the universe became transparent combed the light. It organized its vibrations. It imprinted a faint but definite pattern of polarization onto the CMB. This was a prediction of our standard cosmological model, a known and expected feature of this afterglow. For cosmologists, finding this basic polarization was another spectacular confirmation of theory, but it was also merely the first page of a much more profound text. Because the theory didn't just predict a simple pattern, it predicted that the polarization across the sky could be sorted, decomposed into two fundamentally different types of geometric patterns, two distinct dialects of this secret cosmic language. The first type scientists called E-modes. You can think of these as patterns with a clear defined orientation. They look like lines radiating outward from a point or circling a point. They are smooth, orderly, and possess a kind of geometric parity. E-modes are the expected, the logical, the normal result of density waves of simple compression and rarefaction rippling through the primordial plasma. They are the sound of matter sloshing around in the cosmic cradle, a beautiful but ultimately conventional signature. Observing them would be a feat of incredible technical precision, but they would tell us a story we largely already knew, confirming the details of how matter began to clump together. But there was a second, far stranger, far more elusive pattern predicted. A ghost in the machine. A whisper within the roar. They called this pattern B-modes. Unlike the clean lines of E-modes, B-modes possess a twist, a curl, a vortex. If you were to trace their pattern across the sky, you would find it swirling like a celestial fingerprint or the spiraling eddies in a flowing stream. They have a handedness, a chirality that E-modes completely lack. And this tiny, subtle difference makes them almost impossibly significant. Because the normal physics of the primordial plasma, the simple pushing and pulling of matter, cannot generate these twisting B-modes on a grand cosmological scale. It is a forbidden pattern, a gravitational taboo. To create a swirl in the fabric of polarized light across vast patches of the sky, you need something that can stretch and squeeze space-time itself, and do so with a twisting, shearing motion. You need a force that can literally churn the geometry of the universe. You need the cataclysmic passage of primordial gravitational waves, the colossal ripples from the inflationary epoch, the shock waves of creation, were the only known mechanism that could generate this specific swirling signature. The B-mode pattern was nothing less than the direct, unadulterated shadow of those waves, a faint ghostly image left imprinted on the very first light. To find them would be to find the holy grail of cosmology. It would be like finding the original blueprints of the Big Bang signed by the laws of physics themselves. It would no longer be a theory, no longer an elegant mathematical inference. It would be an observation, a photograph of the birth of time. The search was on. But this was not a task for a conventional telescope. You cannot see B-modes by simply looking up. The signal is infinitesimally faint, buried deep within the noise of the CMB itself, which is in turn buried by the confounding glare of our own galaxy. The signal's predicted strength was a few parts in a billion. It was like trying to hear a single pin drop in the middle of a hurricane from 1,000 miles away. To even attempt such an observation required travelling to the end of the Earth. Scientists needed the coldest, driest, most stable patch of atmosphere on the planet, a place where the air held so little water vapour that it would not absorb or distort the faint microwave signals from space. There is only one such place, the high, desolate plateau of Antarctica, the South Pole, here in the most hostile environment imaginable amid winds that can freeze flesh in seconds, and a darkness that lasts for 6 months of the year. Humanity built its most sensitive ears to listen to the dawn of time. It is a place of profound irony. The most remote location on Earth chosen specifically to get the clearest possible view of the most distant event in history. Among the experiments braving the polar night was a uniquely specialized instrument. Its name was BICEP 2, the second generation of the background imaging of cosmic extragalactic polarization experiment. It was not a majestic structure like the great optical observatories. It looked more like a futuristic cannon, or a cryogenic thermos bottle pointed permanently at a single clean patch of the southern sky. Inside its shielded housing, a revolutionary array of detectors waited. Superconducting antennae cooled to within a fraction of a degree of absolute zero less than 1/4 of a degree Kelvin. At this impossible cold, the inherent thermal noise of the electronics, the random jiggling of atoms that plagues all sensors, was almost entirely silenced. The instrument became a pure crystalline receiver, achieving a sensitivity previously thought to be the stuff of science fiction. For 3 years, from 2010 to 2012, Bicep 2 stared. It did not move. It did not blink. It just patiently, silently collected the ancient light. Photon by photon, it built up a map not of temperature, but of the delicate polarization of the cosmic microwave background. It was a vigil of almost unimaginable patience, an act of profound scientific faith. Faith that the theories were right. Faith that the signature was there waiting to be found. Faith that their instrument was sensitive enough to finally see it. The team led by astronomers John Kovac, Chaolin Kuo and Jamie Bock worked in shifts between the South Pole and their labs back in the United States. The data streamed north, a river of numbers representing the faintest whispers of the cosmos. And the long, agonizing process of analysis began. This wasn't a simple case of developing a photograph. It was a meticulous act of cosmic archaeology. They had to subtract every known source of contamination. They had to account for the faint microwave emissions from our own Milky Way galaxy, the radio noise from distant quasars, the subtle distortions from gravitational lensing. Layer by layer, they peeled back the universe, searching for a pattern, buried beneath a dozen other patterns. It was a process fraught with peril, where the smallest systematic error, the slightest miscalibration of the instrument could create a false signal, a ghost that would fool them into believing they had found what they so desperately sought. They blinded themselves to the final result, working on manipulated data so their own hopes and expectations could not influence the outcome. They checked and rechecked their code, their assumptions, their hardware. They argued, they debated, they tried to prove themselves wrong. For months, the work continued in rigorous self-imposed secrecy. Then, the day came. The day they finally unblinded the data. The day they would look at the real map. In a quiet room, a graph flickered into existence on a computer screen. It plotted the strength of the polarization pattern at different angular scales across the sky. There were data points with error bars representing the uncertainty. And there was a line. A theoretical curve showing what the signal should look like if it were generated by primordial gravitational waves from inflation. The room fell silent. The data points did not just hint at the curve. They did not vaguely suggest it. They fell point after agonizing point directly, perfectly, unmistakably on the line. The signal was not weak. It was not ambiguous. It was powerful, resounding. It was, in the words of one of the scientists, a thunderclap. The characteristic swirling pattern of B-modes was there. The vortex signature, the forbidden curl that only gravitational waves could create, was etched across their map of the infant universe. The team was stunned into a state of disbelief, a feeling that quickly morphed into a tidal wave of pure, unadulterated joy. They had done it. Against all odds, they had seen back to the first trillionth of a second. They had captured the echo of the Big Bang. The secrecy held for a few more excruciating weeks as the team prepared their scientific paper, subjecting their own monumental result to one last round of internal scrutiny. Whispers and rumours began to leak out into the wider cosmological community. Something enormous was coming. Something had been found at the pole. The anticipation built to a fever pitch. And then on March 17, 2014, the world was invited to a press conference at the Harvard-Smithsonian Center for Astrophysics. The room was packed with journalists, scientists and students, an electric current of expectation in the air. John Kovac stood at the podium, his voice steady but betraying a deep underlying emotion. He walked the audience through the experiment, the data, the meticulous analysis, and then he showed the plot. The data points lying perfectly on the curve. He announced to the world that BITEP 2 had directly detected the signature of primordial gravitational waves and the evidence for cosmic inflation. The room erupted, not just with applause but with a palpable collective gasp of wonder. It was a moment that transcends the normal confines of a scientific announcement. It felt historical, foundational. The data suggested the inflationary event was even more violent and energetic than many had dared to dream. The ripples were stronger, the signal clearer than almost anyone had predicted. It was as if the universe had wanted us to find it. News flashed across the globe. It was the lead story everywhere. Echo of the Big Bang. Ripples from the birth of the universe. Smoking gun for inflation found. This was a discovery that touched something primal in all of us. It was the closest we had ever come to an origin story written not in myth or theology, but in the hard empirical language of physics. Theoretical physicist André Linde, one of the original architects of inflationary theory, was shown the results on a video call. His reaction was one of pure, unscripted, tearful joy. Decades of his life's work of abstract mathematics and bold conjecture had suddenly been rendered real visible on a chart of data from Antarctica. He saw the universe confirming his most audacious ideas. The discovery seemed to cement a new standard model of cosmology. It felt like the final triumphant piece of the puzzle had been snapped into place. We now had a direct observational window onto the quantum realm that had governed the universe in its first moments. We had seen the mechanism that blew our cosmos up from a subatomic speck to a vast expanse in an instant, the same mechanism that smoothed it out and simultaneously planted the seeds for all future structure. It was a moment of profound clarity, a peak from which we could seemingly gaze back to the very beginning of everything. The implications were staggering, promising Nobel Prizes and revolutionizing textbooks. For a brief shining moment, it seemed that we, a curious species on a small blue planet, had finally managed to read the first sentence in the autobiography of the cosmos. The universe had spoken, and for the first time we had been able to understand its native tongue. The search, it seemed, was over. The great cosmic question had been answered. A new era of cosmology had with a thunderclap dawned. And so, the celebration was absolute. For a fleeting, brilliant moment in scientific history, it seemed we had done it. We had captured the thunder of creation, the gravitational echo of the universe's first violent shudder. The news ignited the public imagination, a story of cosmic discovery so profound, it felt like the final chapter in our origin story. The graphs were printed, the press conferences held, the champagne bottles emptied. But science is not a destination. It is a relentless, often unforgiving path. And while the world celebrated, a different kind of energy was building within the heart of the physics community. It was not the loud clap of discovery, but the quiet, persistent hum of scrutiny. This is the essential self-regulating mechanism of science, the immune system that seeks out and challenges every new claim, no matter how beautiful or long-awaited. It is a process born not of cynicism, but of a deep collective respect for the truth. The initial euphoria, that pure, unadulterated intellectual joy, began to give way to the meticulous, painstaking work of peer review. Questions at first whispered in university corridors and then posted on academic forums began to coalesce into a formidable counter-narrative. Was the signal really so clean? Could the team at the South Pole, in their determined focus on one small, supposedly pristine patch of sky, have missed something? The BITEP 2 instrument was a masterpiece of precision, a lens sharpened to an unprecedented degree. But what if the problem wasn't the lens, but a nearly imperceptible film of dust lying upon it? What if the ghost they had found was not from the dawn of time, but from our own cosmic backyard? The doubt began to centre on a confounding and beautiful suspect, a substance as common as it is complex, interstellar dust. This isn't the mundane dust that gathers on your bookshelf. This is the ancient recycled ash of long-dead stars, a fine smoke of carbon and silicate grains scattered throughout the Milky Way. It is the raw material for future suns, the stuff of nebulae, the very substance from which new worlds are born. And crucially, this cosmic dust is not inert. It is a dynamic, electrically charged medium, a vast shimmering veil that drifts on the galaxy's magnetic winds. Imagine countless trillions of microscopic oblong grains of dust, each one a tiny compass needle. Sweeping through the grand arcing magnetic field of the Milky Way, these grains align themselves in unison, like iron filings around a bar magnet. This collective alignment turns the entire dust cloud into a massive polarized filter. As these grains absorb and then re-radiate heat in the form of microwave light, that light carries with it a signature of their shared orientation. It becomes polarized light, and when viewed through the exquisitely sensitive eyes of a telescope like BICEP 2, this light from galactic dust could produce a swirling pattern, a B-mode polarization that was a terrifyingly perfect mimic of the signal from primordial gravitational waves. The universe, it seemed, had set the most elegant of traps. It had created a cosmic forger and imposter so convincing that it could masquerade as the echo of creation itself. The BICEP 2 team knew about dust, of course. They had chosen their deep field patch of the sky, the southern hole, precisely because it was thought to be one of the cleanest windows onto the early universe, a region with minimal galactic foreground contamination. They had used the best available models at the time to estimate the level of dust polarization and subtract it from their data. Their conclusion was that the dust contribution was negligible, a tiny fraction of the colossal signal they were seeing. Their data screamed that this was new physics, that this was the real thing. But the existing models of galactic dust were just that, models. They were extrapolations, educated guesses based on limited data. What the scientific community desperately needed was not a model, but a map, a definitive high-resolution all-sky atlas of this shimmering polarized veil. And as it happened, that very map was being meticulously pieced together by another far more comprehensive eye in the sky. Orbiting silently at a gravitationally stable point 1 million miles from Earth, the European Space Agency's Planck satellite was the ultimate cosmic cartographer. Unlike BICEP 2, which was designed to stare deeply at one tiny spot, Planck's mission was to scan the entire celestial sphere again and again. Its goal was to create the most complete picture of the cosmic microwave background ever assembled, but to do that, it first had to systematically identify and characterize every single thing that stood in the way. It had to map every source of microwave light in the universe, from nearby galaxies to the faint polarized glow of our own Milky Way's dust. The Planck team, a global consortium of hundreds of scientists, had been living with this data for years. They understood its subtleties, its complexities and its deceptions better than anyone on the planet. They were not focused on the BICEP 2 announcement itself, but on the painstaking process of releasing their own full analysis of galactic foregrounds. As the debate over the BICEP 2 result intensified, it became clear that the key to unlocking the truth lay in combining these two extraordinary data sets. What followed was a period of intense, sometimes tense scientific diplomacy. The BICEP 2 team, which had by then merged with the nearby Keck Array experiment, held the deepest, most sensitive map of B-mode polarization in one small patch of the sky. The Planck team held the shallow but all-encompassing map of the dust that permeated the entire galaxy, including that very same patch. Neither dataset alone could provide the definitive answer. A collaboration was essential. It represented the scientific method at its most raw and most noble, two competing brilliant teams setting aside the race for glory to embark on a joint unfiltered search for the ground truth. They had to cross-correlate their maps, laying one on top of the other. It was a moment of profound suspense for the entire cosmological community. If the BICEP 2 signal was truly primordial, its pattern should have no correlation with the pattern of dust emission mapped by Planck. The two images would look completely different. One a chaotic swirl from the Big Bang, the other a structured glow from the Milky Way. The teams worked for months, carefully checking and rechecking every calculation, every statistical assumption. The fate of a Nobel Prize-worthy discovery hung in the balance. When they finally overlaid the two maps, the result was unambiguous and for many heartbreaking. The patterns matched. They didn't just rhyme, they were nearly identical. The swirls and eddies detected by BICEP 2, the very patterns hailed as the first tremors of space-time, lined up with breathtaking precision with the swirls and eddies of polarized dust emission measured by Planck. The conclusion was inescapable. The powerful B-mode signal was not from the beginning of time. It was not a gravitational wave. It was dust. It was the glow of our own galaxy fooling us into believing we had seen the face of creation. The data analysis revealed that the initial models had dramatically underestimated how much the dust in this clean patch of sky was polarized. Once the full measured contribution from the dust was subtracted, the colossal primordial signal vanished. It shrank away, leaving behind only noise and a new, much smaller upper limit on what the real signal could be. The retraction when it came was a solemn and difficult moment. It was the public unwinding of a discovery that had electrified the world. For the scientists on the BICEP 2 team, it was a moment of profound professional and personal disappointment. They had followed the data, they had been meticulous, and they had been courageous in their announcement. But nature in its infinite complexity had been more subtle than their models had allowed. Yet to call this a failure is to fundamentally misunderstand the nature of science. This was not a failure. It was a demonstration of its greatest strength. The system had worked. A bold claim was made, it was subjected to intense scrutiny, new data was brought to bear, and the initial conclusion was revised in the light of better evidence. It was a painful, public and powerful example of scientific self-correction. In falling short of its grandest ambition, the BICEP 2 experiment had provided the entire field with something almost as valuable, a crucial hard-won lesson. It had inadvertently created the most precise map of polarized dust ever made for a patch of sky, providing a critical calibration point for all future searches. The entire episode transformed the quest for primordial gravitational waves. The age of innocence was over. The hunt had become exponentially harder, the challenge far more complex than previously imagined. We now understood that we weren't just searching for a whisper in a quiet room. We were trying to hear a whisper in the middle of a cosmic symphony, a cacophony of foreground signals from our own galaxy. The Milky Way, once just the beautiful backdrop to our observations, was now revealed as the primary obstacle, a luminous fog that must be understood and navigated with almost supernatural precision. The challenge shifted from simply building more sensitive detectors to also developing vastly more sophisticated methods for cleaning the data. It was no longer a simple matter of looking. It was now a grand challenge in signal processing and painstakingly untangling multiple overlapping sources of polarized light. To find the echo of the Big Bang, you first had to perfectly map model and subtract the light of 100 billion nearby stars and all the dust that drifts between them. This new, more sober reality gave rise to a new generation of experiments designed from the ground up to meet this formidable challenge. The lessons from BICEP 2 and Planck were forged into the very architecture of their successors. These new observatories would combine the strategies of both pioneers, the deep targeted stare of BICEP 2 with the multi-frequency, foreground mapping power of Planck. By observing the same patch of sky in many different microwave colours, scientists can distinguish the signal of the CMB from the signal of galactic dust. The CMB spectrum is famously consistent, a perfect blackbody curve across all frequencies. Galactic dust, however, glows more brightly at higher frequencies. By measuring the B-mode polarization at say 5 or 6 different frequencies, you can track precisely how the dust contribution changes and then subtract it with mathematical confidence, isolating the single achromatic signal from the early universe that remains unchanged beneath. This is the strategy being employed by a global fleet of new instruments, a coordinated assault on the problem from multiple fronts. In the high dry air of the Chilean Atacama Desert, the Simons Observatory and the Atacama Cosmology Telescope are deploying thousands of new detectors, each a tiny superconducting circuit cooled to a fraction of a degree above absolute zero. They are scanning the sky with an unprecedented combination of sensitivity and frequency coverage, designed to peel back the galactic veil layer by layer. And on the horizon looms the ultimate instrument in this quest, a project of monumental scale and ambition known as CMB-SCR, or Cosmic Microwave Background Stage 4. This isn't just a single telescope, it is a vision for a unified global effort combining the resources of multiple national agencies and universities. It will involve a vast army of telescopes both in Chile and at the South Pole working in concert. CMB-S4 represents a brute force approach born of hard-won wisdom. It will deploy not thousands, but over 500,000 detectors, an order of magnitude more than any preceding experiment. This colossal network will function as a single, planetary-scale eye, staring at the sky for years on end. Its goal is to measure the polarization of the CMB with such exquisite, overwhelming sensitivity that it can either finally definitively detect the faint residual signature of primordial gravitational waves or prove with near certainty that the simplest models of cosmic inflation are incorrect. The disappointment of 2014 did not end the search. On the contrary, it clarified the stakes, hardened the resolve, and illuminated the precise path forward. We now know the monster we are hunting, and we know the intricate deceptions of the terrain. The quest for the ripples of creation has become a multi-generational epic, a testament to our stubborn refusal to accept the limits of our vision. Armed with the painful lessons of the past and the powerful tools of the future, we are turning our eyes back to the sky, not with the naive optimism of before, but with the focused, unyielding determination of a community that has stared into the fog and is now ready to finally see through it. The dream had flickered, but it did not die. Out of the humbling ashes of premature celebration, a new kind of hunt was born, forged in the crucible of caution. The age of the lone observatory making a solitary claim was over. We had been taught a harsh and necessary lesson by the cosmos that the universe does not give up its deepest secrets easily. The siren song of cosmic dust, a perfect mimic of the primordial signal, had shown us the profound challenge that lay ahead. It was a challenge not of sensitivity alone, but of certainty. To hear the whisper of creation, we first had to silence a galaxy of noise. This new era would be defined by one singular principal collaboration. No longer would one telescope stare into the void. Now a global network of instruments would act as a single planetary eye, their data streams weaving together into an unprecedented tapestry of evidence. This is the story of that final meticulous assault on the cosmic dawn, the relentless Herculean effort to peel back the last veil and gaze upon the face of the infant universe. The quest moved to the most extreme desolate places on Earth, locations chosen for their hostility to life and their kindness to light. High in the Chilean Atacama Desert at over 17,000 feet, the air is so thin and dry that it is almost a window into space. Here a new generation of cosmic cartographers began their work. The Simons Observatory, a breathtaking assembly of cutting-edge telescopes, rose from the ochre dust like a shrine to the Big Bang. It wasn't just one instrument, but a coordinated array, each telescope optimized for a specific task in this grand cosmic filter. Some are designed to map vast swathes of the ancient sky, with broad strokes identifying the largest, most ancient curls of polarized light. Others are built to zoom in with astonishing precision to scrutinize the finest details of the microwave tapestry. Their combined power represents a quantum leap in our ability to see the faint frozen echoes of the universe's first moment. And 10,000 miles away at the very bottom of the world, the vigil at the South Pole continued more ambitious than ever. Here at the coldest, driest, most stable outpost on the planet, the Bicep Keck Array, the very experiment that had tasted false victory was rebuilt, expanded and refined, its mission reborn. Joined by the powerful South Pole telescope, this polar armada stares into the cleanest patch of sky accessible from our world, a celestial window relatively free of the Milky Way's confounding glare. For months on end during the unending darkness of the Antarctic winter, these robotic sentinels patiently drink in the ancient light, collecting photons that have been travelling towards us for 13.8 billion years. The goal of these terrestrial giants is a project of breathtaking scale CMB S4. The S4 stands for Stage 4, the ultimate ground-based experiment, a plan to merge the efforts in Chile and the South Pole into a single, overwhelming force. It will deploy not thousands but 500,000 detectors, an army of superconducting sensors that will map the CMB with such fidelity that it would be like measuring the height of every ripple on Earth's oceans down to the thickness of a single human hair. The sheer volume of data is almost incomprehensible, a torrent of information that will require supercomputers years to analyse. Yet even these magnificent terrestrial endeavours are not enough. Our own atmosphere, however thin, remains a shimmering turbulent curtain. To achieve the ultimate purity of vision, we must leave our world behind. From the silent vacuum of space, a new hunter is being prepared, Lightbird. The Lightbird satellite, a mission led by Japan with international partners, is an instrument of exquisite and singular purpose. Freed from the distortion of Earth's air and weather, it will float in the cold, stable darkness of a Lagrangian point, a gravitational oasis, 1,000,000 miles from home. It will scan the entire sky, not just small patches, and it will do so across 15 different frequency bands. This is the crucial weapon in the war against uncertainty. Because the great challenge is no longer just seeing something, it's knowing with unimpeachable certainty precisely what you are seeing. Imagine you are in a grand concert hall trying to hear the delicate hum of a single tuning fork struck once at the beginning of the performance. But since that first faint tone the entire orchestra has begun to play, there are the thunderous drums of nearby supernovas, there is the soaring string section of spiraling electrons in our galaxy's magnetic fields, there is the blaring brass of hot glowing dust clouds the very sound that once fooled us into thinking we'd heard the prize. All of these foregrounds, this cacophony of cosmic noise, are hundreds, thousands, even millions of times louder than the primordial signal you are desperate to isolate. How do you find that one pure note in the overwhelming symphony? You listen with an instrument that can distinguish colour. The primordial hum of gravitational waves from inflation has a unique spectral signature. It behaves like a perfect black body, its intensity changing with frequency, in a very specific, predictable way dictated by the laws of thermodynamics. But the noise does not follow this rule. The synchrotron radiation from electrons, for instance, gets dramatically fainter as you listen at higher and higher frequencies. The thermal emission from galactic dust does the opposite. It glows brighter and brighter at higher frequencies. Each source of noise has its own distinct colour, its own spectral fingerprint. This is the key that unlocks the entire puzzle. By observing the sky with multiple eyes, each tuned to a different frequency, scientists can begin the painstaking work of deconstruction. An observatory like Simon's or a satellite like Lightbird doesn't just take one picture of the sky. It takes many simultaneous pictures, each one a map of the heavens, as seen in a different slice of the microwave spectrum. In one image, the dust might scream out a blazing curtain of light. In another, taken at a much lower frequency, that same dust is a transparent ghost, while the synchrotron hiss now dominates the view. The primordial signal, the true echo of the Big Bang, is the only component that will be present in every single image, its intensity shifting in that one characteristic blackbody curve. The process is a form of celestial archaeology executed with algorithms. Computers take these multi-frequency maps and build a model, a precise three-dimensional reconstruction of all the contamination. They learn the exact shape, temperature and polarization of every dust cloud. They map the intricate web of our galaxy's magnetic fields. They create a perfect template of the noise, and then with mathematical precision that is almost magical, they subtract it. Layer by layer, they digitally peel away the foregrounds, stripping the cosmic static from the ancient broadcast. First, the brightest, most obvious sources of contamination are removed. Then the fainter, more diffuse galactic haze is carefully modelled and erased. They even account for the faint microwave glow of asteroids in our own solar system. With each step, the universe grows quieter. The roar of the orchestra fades and we lean in closer listening. To enhance this process, we rely on a ghost in the machine, the Planck satellite. Though its mission is complete, Planck's legacy is the ultimate treasure map of contamination. It gave us the most complete all-sky survey of cosmic dust ever created. This map is now a foundational tool for every ground-based experiment. Scientists can overlay the Planck data with the new higher resolution maps from observatories like Bicep Keck and the Simons Observatory. By cross-correlating the information, they can see exactly how the dust seen by Planck in one patch of sky behaves in the deeper, more sensitive new data. This allows them to refine their subtraction models with incredible accuracy, ensuring they are not accidentally removing the very signal they seek. It is a system of checks and balances written into the very fabric of the search. One experiment's potential discovery is immediately vetted against another's map of noise. This global interconnected web of data ensures that any future claim will be built upon a foundation of granite, not sand. But all the clever algorithms in the world are meaningless if the instruments themselves are not sensitive enough to detect the signal. And at the heart of this technological marvel is a device that borders on science fiction, the Transition Edge Sensor, or TES. These are the quantum eyes that actually see the ancient light. Imagine a tiny square of metal smaller than a pixel on your screen chilled to within a 10,000th of a degree of absolute zero. At this impossible temperature, it becomes a superconductor, losing all electrical resistance. Scientists then use magnetic fields to nudge its temperature ever so slightly upwards, placing it on the razor's edge, the transition edge, between being superconducting and being just barely resistive. It is a state of exquisite, almost unnatural instability. When a single photon from the cosmic microwave background, a particle of light that has travelled across the entire observable universe, finally ends its journey by striking this tiny sensor, its minuscule energy is just enough to tip the balance. The sensor warms by a millionth of a degree, its resistance flickers, and a hypersensitive magnetic field detector called a squid registers the change. We have in effect built the most sensitive thermometer in existence to take the temperature of the Big Bang itself, and we are not building one of them. We're building hundreds of thousands. Each one of these detectors is coupled to a tiny antenna etched onto silicon wafers with photolithographic techniques borrowed from the computer chip industry. Some are sensitive to vertically polarized light, others to horizontally polarized light. By combining their signals, astronomers can reconstruct the faintest twist, the elusive B-mode polarization, in the incoming radiation. It is a brute force approach born of necessity. The signal is so faint, so utterly buried in random quantum noise, that the only way to find it is through the law of large numbers. By averaging the measurements from hundreds of thousands of detectors over thousands of hours of observation, the random noise begins to cancel out while the faint, coherent signal, the true gravitational curl, slowly begins to emerge. It is like trying to see a single organized ripple in a stormy sea by taking millions of snapshots and averaging them together. The random chaotic waves eventually smooth into a grey blur, but the persistent underlying swell, if it exists, will remain. This is where we stand today, at the bleeding edge of technology and the outer shore of the known. The first layers of noise have been stripped away. The blaring symphony of the Milky Way is being quieted frequency by frequency. The data from the Atacama from the South Pole and from past space missions is being woven together into a single coherent vision of the early universe. We are pushing past the known contaminants and into a new realm of uncertainty, a place where the remaining noise is itself a mystery. Are there other more subtle foregrounds we haven't yet accounted for? Is the very dust we are trying to subtract more complex than our models assume? Or are we now simply battling the fundamental noise of our own detectors, the unavoidable quantum hiss of reality itself? The signal, that final definitive proof of inflation, the echo of the universe's violent birth, now lies hidden in this penumbra. We are so close. The sensitivity of our current and upcoming experiments is now crossing a critical threshold. The theories of inflation born from the minds of physicists decades ago do not just predict that these gravitational waves exist, they predict their amplitude, their strength. Most mainstream models predict a signal that is just strong enough to be found by the instruments we are now deploying. We are for the first time poised to make a definitive statement. We have peered into the abyss, and the abyss is beginning to resolve. The culmination of a century of cosmology is at hand. Einstein's most exotic prediction, born from a simple thought experiment. Goethe's audacious theory scribbled on a notepad late one night. The life's work of thousands of scientists, engineers, and dreamers. All of it has led to this moment, to this final painstaking search through the fading static of creation. This is more than just a confirmation of a theory. A detection would be the single greatest achievement in observational cosmology. It would be like finding a fossil from the first trillionth of a second of time. We would no longer be merely inferring the existence of the inflationary epoch. We would be observing its direct physical consequence. We would have an energy probe into a realm of physics so extreme it makes the Large Hadron Collider look like a child's toy. The strength of the signal would tell us the precise energy scale of inflation, revealing the physics that governed reality at 10 to the minus 36 seconds. It would be our first tangible glimpse into the unification of gravity and quantum mechanics, the holy grail of modern physics. We would be opening a window not just on the birth of space and time, but on the very quantum substrate from which they emerged. A world previously confined to the chalkboards of theorists would suddenly become an observable, measurable place. We are standing on a precipice holding our collective breath. The data is streaming in from the coldest, highest places on Earth. The algorithms are running. The noise is being stripped away. And we are listening with all of our accumulated knowledge and technology for a sound that has been travelling towards us since the beginning of all things. What will we hear when the universe is finally quiet enough? Will we hear the faint ghostly hum of space-time itself, shaking from the violence of its own creation, or will we be met with silence? And so, here we stand. After a century-long odyssey that began in the mind of a single man, and has since culminated in a global symphony of science, we find ourselves on the ultimate precipice. We have journeyed from the quiet solitude of Einstein's equations, through the thunderous predictions of cosmic inflation, to the construction of the most sensitive instruments ever conceived by humankind. Arrayed across the frozen wastes of Antarctica, the high deserts of Chile, and soon orbiting in the silent void of space, these technological ears are pressed against the deepest wall of time listening. They are straining to hear not just an echo, but the resonance of the act of creation itself. For 100 years, we have been charting the shoreline of a cosmic ocean, whose existence was only ever inferred. We have mapped its currents and tides through the cosmic microwave background, through the dance of galaxies and through the violent collisions of black holes. But now we are waiting for a message from its deepest abyss, a message that has been travelling toward us since the very first moment of existence. We have followed this trail of celestial breadcrumbs back through 13.8 billion years of cosmic history, past the formation of our own solar system, beyond the birth of the Milky Way, and past the ignition of the very first stars. We have pushed our understanding to the edge of the observable, to that opaque wall of plasma 380,000 years after the beginning, a point beyond which no light can ever reach us. Yet this is not the end of the road. It is merely the final barrier to our conventional sight. Because gravity, as we have discovered, speaks a different language. It is a language that was uttered in the universe's first incandescent breath, a language that space-time itself has never forgotten. We are on the verge of becoming literate in this primordial tongue. The search for these gravitational waves, these fossilized ripples from the Big Bang, has been a multi-generational relay race of intellect and ambition, a testament to our species' relentless need to know where we came from. It is a quest that has unified thousands of minds across dozens of nations, all focused on detecting a signal so faint a whisper, so ancient, it represents the energetic equivalent of a single feather dropping on the surface of the moon. The stakes of this monumental effort are almost impossible to overstate. This isn't simply about adding another discovery to the textbooks, or refining the parameters of our existing models. It is about a fundamental shift in our perception of reality, a moment of contact with the physics that govern the genesis of everything we know. Finding this signal would be akin to an archaeologist discovering not just a fossil, but a recording of the moment life first sparked into existence. It is the universe's birth certificate, and we are finally learning how to read the signature. The quiet hum of supercomputers processing petabytes of data from our telescopes is the sound of us holding our collective breath. With every passing day, with every refined analysis, we inch closer to an answer. Will we hear the faint ghostly strain of creation's opening chord, or will the universe's beginning remain shrouded in an impenetrable silence? The answer, whichever way it falls, will define the future of cosmology, and in a very real sense the future of our understanding of our own place within this grand unfolding narrative. We are poised not just to witness history, but to witness the very beginning of it. To finally detect this primordial gravitational background would be first and foremost the definitive vindication of cosmic inflation. For decades, inflation has been the most elegant and powerful explanation for the universe we see today. It's a theory that brilliantly solves the puzzles our standard Big Bang model could not, explaining why the universe is so remarkably flat, why distant regions look so uncannily similar, and where the initial seeds of cosmic structure came from. Yet for all its explanatory power, it has remained just that, a theory. A beautiful, compelling, and widely accepted story, but a story nonetheless. The detection of these specific gravitational waves would transform that story into documented fact. It would be the empirical bedrock upon which the entire inflationary paradigm could finally rest unshakable. Because these waves are not just a byproduct of inflation, they're its unique, non-negotiable fingerprint. The cataclysmic, faster-than-light expansion of space-time in that first sliver of a second would have violently stretched and squeezed the quantum vacuum, generating a storm of gravitational ripples with a very specific signature. This signature, a particular twisting pattern of polarization in the cosmic microwave background known as B modes, can be produced by nothing else we know of in the early universe. It is a smoking gun of cosmic proportions. To find it would be to prove that the universe did indeed begin with this unimaginable burst of hyperexpansion, a moment when it swelled from a size smaller than a proton to larger than a grapefruit in less than a trillionth of a second. Suddenly, that abstract concept would become a concrete historical event as real as the formation of the Earth or the extinction of the dinosaurs. We would no longer have to speculate. We would know. We would have a direct observational window into the mechanics of that first explosive moment, allowing us to measure the energy scale at which inflation occurred. This wouldn't just confirm the what of inflation, but the how. The amplitude or strength of these waves would act as a cosmic speedometer, telling us precisely how fast and how violently the universe expanded. It would allow us to test and distinguish between the hundreds of different inflationary models that theorists have proposed, winnowing down the possibilities to only those that match the data written across the sky. Think of it as the ultimate seismograph. Just as geologists use seismic waves to understand the forces at work deep inside our planet, cosmologists would use these gravitational waves to probe the physics of the universe's core engine. We would be analysing the tremors of the Big Bang itself. This confirmation would cascade through all of physics, solidifying our entire cosmological framework. The seeds of galaxies, the vast cosmic web of dark matter, the grand tapestry of clusters and superclusters, all of it traces its lineage back to the tiny quantum fluctuations that inflation stretched to astronomical scales. Without inflation, the origin of these structures is a deep mystery. With the evidence of primordial gravitational waves, that mystery would evaporate, replaced by a clear causal chain of events stretching from the quantum realm of the infant universe to the magnificent celestial structures we inhabit today. We would have found the first page of the cosmic blueprint, the architect's original drawings for the cosmos. The search is not just for a faint signal, it is a search for our own ultimate causal origin, the confirmation of the mechanism that made our existence possible. But the implications of such a discovery would reach far deeper, plunging us into a realm of physics so extreme it has never been accessible to us before. The energy levels at which inflation is thought to have occurred are a quadrillion times higher than anything we can achieve in our most powerful particle accelerators, like the Large Hadron Collider. At these biblical energies, the universe was a fundamentally different place. The very laws of physics as we know them were still being forged. It was a time when the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces were not distinct. Theory predicts that in this primordial crucible, three of these forces were unified into a single symmetrical grand unified force. Primordial gravitational waves would be our only direct probe of this era. They would be messengers from a physical reality we can never hope to recreate on Earth, carrying invaluable information about how the universe operated when it was less than a sextillionth of a second old. These waves would give us a spectral analysis of the universe's birth. By studying the precise shape and features of their frequency spectrum, we could uncover clues about the particles and fields that existed during that epoch. We could potentially see evidence of the grand unification symmetry breaking the exact moment when the strong nuclear force split off from the electro-weak force, an event that fundamentally shaped the physics of our universe. It would be like analysing the light from a distant star to determine its chemical composition, except here the light is gravity, and the star is the entire universe in its nascent state. This is the holy grail for both cosmologists and particle physicists, the unification of the very large with the very small. For decades, these two pillars of modern physics have developed in parallel, each describing its own domain, with incredible accuracy, but without a coherent bridge between them. Primordial gravitational waves could be that bridge. They are a phenomenon born from quantum mechanics on a cosmological scale, the perfect embodiment of quantum gravity. Finding them would open up an entirely new field of science, gravitational wave archaeology. We could search the background for subtle anomalies, for tiny bumps and wiggles in the signal that might indicate other exotic events that occurred during those first moments. Did cosmic strings, theoretical one-dimensional defects in space-time form and decay? Did the universe undergo multiple phases of inflation? Did other unknown particles exist in the primordial plasma? Each of these hypothetical events would leave its own faint, unique imprint on the gravitational wave background, a ghostly echo waiting to be deciphered. We would be moving from a period of confirmation to one of pure exploration. We would be mapping a new continent of physics, one that exists not in space, but at the very beginning of time. The discovery would not be an endpoint, but the grand opening of a new frontier, providing decades, perhaps centuries of new data, to pore over new questions to ask and new mysteries to unravel about the fundamental operating system of reality. This journey inevitably leads us to an even more profound question, one that strikes at the very heart of our existence. What is space-time? We have spent our entire history living within it, moving through it, but we have only ever been able to study its properties in the relatively calm, gentle conditions of the modern universe. Detecting the gravitational waves from the Big Bang would give us a glimpse of space-time in its most extreme state, its birth. It would be our first empirical handle on the process that created the very stage on which the cosmic drama unfolds. Was space-time, as Einstein's theory suggests, born in the singularity of the Big Bang bursting into existence, along with matter and energy, or is it something more fundamental, something that perhaps predates the Bang? Some speculative theories like string theory or loop quantum gravity propose that our universe's beginning was not a true singularity, but a big bounce, a transition from a prior contracting cosmic phase. These different origin scenarios would produce subtly different gravitational wave signatures. A universe born from a bounce might have a gravitational wave background that is suppressed at very long wavelengths, a distinctive cutoff that would be a telltale sign of pre-Big Bang physics. To find such a feature would be utterly revolutionary. It would mean our universe is not a singular creation, but perhaps part of an eternal cycle of expansion and contraction. It would shatter the concept of a singular beginning to time itself. We would be forced to confront the possibility that our cosmos is just one chapter in a much older, perhaps infinite story. Furthermore, these primordial ripples could hold clues to the dimensionality of space-time. Some advanced theories designed to unify gravity with quantum mechanics predict the existence of extra hidden spatial dimensions. During the immense energies of the inflationary epoch, these extra dimensions could have influenced the production of gravitational waves, leaving a faint anomalous signature in their spectrum. Discovering such a signature would be irrefutable proof that the reality we perceive with its 3 dimensions of space and one of time is merely a shadow of a much richer, higher dimensional existence. We would be like the 2-dimensional inhabitants of Edwin Abbott's Flatland, finally seeing evidence of a 3rd dimension, a revelation that would forever alter our perception of the world. The fabric of reality would suddenly appear deeper, more complex and more mysterious than we ever imagined. These primordial whispers are not just carrying information about the matter and energy that fills the universe. They are carrying information about the very container itself. They are the resonating vibrations of the cosmic drumhead, and by listening to its tone and timbre, we can finally begin to understand what it is made of, how it was forged, and whether it has limits beyond what our senses can perceive. The detection of these waves is not just about looking back to the beginning of our universe. It is about looking beyond the known boundaries of reality itself. It's an opportunity to ask the deepest possible questions about the nature of existence, and for the very first time to expect an answer backed by observational data. And perhaps the most staggering implication, the one that truly pushes the boundaries of imagination, is that these waves could offer the first tangible evidence for the existence of the multiverse. The theory of eternal inflation, a natural extension of the basic inflationary model, suggests that what we call the Big Bang wasn't a one-time event. Instead, our universe may be just one bubble that nucleated out of a vast, eternally inflating metaverse, with countless other universes constantly popping into existence, each potentially with its own different laws of physics. For decades, this has been a tantalizing but untestable idea, belonging more to the realm of philosophy than to empirical science. primordial gravitational waves could change that forever. If our universe is indeed one bubble among many, it's possible that in its earliest moments it may have collided with another bubble universe. Such a cataclysmic event would have sent a shockwave of gravitational energy propagating through our space-time. This shockwave would leave a specific asymmetric pattern imprinted on the primordial gravitational wave background, a kind of cosmic bruise. It would appear as a circular spot on the sky, where the gravitational waves were slightly stronger or had a different polarization characteristic. Finding such a pattern, a disk of doom, as some physicists have called it, would be the most profound discovery in the history of science. It would be the first piece of evidence that our cosmos is not unique, that we are part of a far grander and more complex reality than we have ever conceived. The philosophical and existential impact would be immeasurable. Our entire universe, with its billions of galaxies and trillions of stars, would be revealed as just a single grain of sand on an infinite cosmic beach. It would be the ultimate Copernican revolution, displacing not just the Earth from the centre of the universe, but our entire universe from the centre of existence. This is the precipice on which we now stand. We are listening for the echoes of creation, not only to understand our own origins, but to potentially discover the existence of realities beyond our own. The search for primordial gravitational waves has become a search for the very limits of what is knowable. It is a testament to the power of the human mind to conceive of such possibilities, and to build machines capable of testing them. Whether we find evidence for other universes or not, the mere act of pushing our instruments and our theories to this ultimate boundary is a triumph. We are daring to ask the most fundamental questions armed with the tools of science, and the universe in its boundless complexity may be on the verge of providing an answer. So when we look up at the night sky, we're no longer just looking at a static snapshot of the present. We are looking at a history book written in light and gravity, and in the faint invisible hum that permeates all of space, we may soon find the book's missing first chapter. The detection of primordial gravitational waves will not be an end. It will not be the final answer that closes the book on cosmology. Instead, it will be the key that unlocks a whole new library. It will mark the end of our cosmic amnesia the moment we finally remember how we began. These ripples of creation, this fossilized sound from the Big Bang, represent the ultimate connection to our own genesis. They are the final, unredacted page of our origin story, telling us that we are the children of a reality, forged in an instant of unimaginable violence and breathtaking beauty. The story is written across the entire sky, a silent, patient testament to the beginning of everything. And we, after 13.8 billion years of cosmic evolution, are finally ready to read it.